Welcome to my classroom. I will talk about two methods on solving equations for numerical answers. These two methods were included in the past curriculum, but removed from the current DSE syllabus. The first one is bisection method, which was taught in third level math. The second one is Newton method, which was discussed in A-level applied math. So this video is for those who want to learn more techniques on solving equations. One of the core discussion of the math curriculum in secondary school is to solve equations. In Form 1, we learn how to solve linear equations in one unknown, which serve as the base of the further discussion, as many equations we learn later on can be reduced to linear equations. In Form 2, we learn the system of linear equations in two unknowns. The system can be solved by substitution or elimination. These algebraic methods give exact solutions and usually are the main choices of the working in the exercise. The system can also be solved by drawing the graphs of the equations. The graphical method visualizes the equations as straight lines, and the intersection gives an approximate solution to the system. In Form 3, the power of the equations increases to 2. We talk about quadratic equations in one unknown. We factorize the equations into a product of two linear factors, and thus the equations can be solved by the techniques learned in Form 1. In Form 4, we learn further techniques for solving quadratic equations which cannot be factorized. The technique of computing the square is summarized as the quadratic formula, which can be applied to all quadratic equations. In other words, we are able to find the exact solutions of any quadratic equation. We also visualize quadratic equations as parabola. By sketching the graph, approximate solutions of quadratic equations can be obtained. With the experience of solving equations, we see the development of number systems. Up to Form 3, we have natural numbers, integers, and rational numbers. With quadratic formula, we have irrational numbers or real numbers and complex numbers. In Form 4, we also learn how to solve polynomial equations with higher powers. The idea is to apply factor theorem to find a rational root and then reduce the power of the equation by division. We are given a number of exercises that the polynomial equations can finally be reduced to quadratic equation, so that the original equation is completely solved. Yet, it is easy to expect that this successful experience is limited to a part of polynomial equations. When the roots of an equation are all irrational or complex with imaginary part, factor theorem cannot be applied, and thus the equation cannot be reduced to a lower power. In other words, the mechanism of this method fails. Are we able to solve such equations then? The answer is positive. We can make use of graphical method, but due to the limitation of curve sketching, the solution so obtained can only be an approximation with a low precision. If we want to have an approximate solution with a higher precision, we need further techniques. And it is the theme of this video. Let me use an example for illustration. Suppose we want to solve the cubic equation. For easy discussion, let f(x) be. As the leading coefficient is 1 and the constant term is -4, we can check the function value at x equals for possible linear factors of f(x), that is, possible rational roots of the equation. We have all of them are non-zero. That means there is no rational root. In other words, all roots are irrational or complex with imaginary part. The previous mechanism fails. We notice that the function f(x) is a continuous function on all real numbers, and the function value swap the sign between x equals 1 and x equals 2. Therefore, The equation f(x) equals 0 has a real root between 1 and 2, and this root is an irrational number. Let us look for this root corrects to 3 significant figures. The idea of bisection method is first to locate an interval containing a real root of the equation. This can be done by checking the function value at the endpoints of the interval, which are opposite in sign. In our example, the interval is 1, 2, where f1 is negative and f2 is positive. The second step is to narrow down the interval by taking the midpoint of the interval and check which half of the interval containing the root. Repeat the process until both endpoints of the interval give the same value under the required position. Thus, we take the midpoint of 1 and 2 and get 1.5. Check the value f of 1.5, which is negative. That means the roots lie in the upper part of the interval. Repeat the process, take the midpoint and get 1.75. Check the value, which is positive. So, the roots lie in the lower half of the interval. Both endpoints of the intervals are not the same. The process goes on. Let me record the results in the following table. Take the midpoint and have 1.625. Evaluate the function at the midpoint and gets a negative value. Thus, the midpoint replaces the left end of the interval. Find the midpoint again and check the sign of the function value at the midpoint, which is positive. So the midpoint replaces the right end of the interval. The process goes on. Now, both endpoints give 1.65 when rounding off to 3 significant figures. That is, the root is 1.65 corrects to 3 significant figures. You may notice that the function value is calculated several times at different points. To make the calculation a bit easy, it is good to program the function in your calculator before the actual calculation. For Casio FX50FH, here are the steps and key-in sequence of the program for your reference. If you find the midpoints are too lengthy for working, you may trim the numbers to say 5 significant figures for further calculation and record. The choices of midpoints are not rigid. The main idea is to find a point in the interval to narrow down the length of the interval, squeezing the value of x with the expected position. Here is a table with simplified numbers. The bisection method is easy for understanding with simple calculation. Yet, it may take a little more steps for getting the answer to the required position. Here is another method. Newton method is relatively faster, but it needs more techniques from calculus. Again, the function taken from the equation is expected to be continuous. The curve is smooth enough so that it is differentiable. That is, the derivative exists. Let me first explain the idea of the method. Suppose we want to solve the equation f(x) equals 0. Assume the curve of y equals to fx cuts the x-axis at the point p alpha 0. That is, alpha is the solution of the equation. Our target is to find the value of x, which is close to alpha, to the required position. We try to locate a point on the curve where the x-coordinates of A is x1, and x1 is close to alpha. Use the derivative. We can find the slope of the tangent to the curve at A. By point-slope form, we have the equation of the tangent at A. Suppose the tangent cuts the x-axis at x equals to x2. We have, make x2 as the subject. Repeat the process. Consider the tangent at B, where x equals to x2, and obtain x3, which is closer to the root alpha. In general, for the n rounds, we have, by iteration, we can obtain the value of x, which is close to the root alpha, to the required precision. Let me illustrate the working with the previous example. Find the derivative of fx. Then, the iteration formula is, take x1 equals 2. Program the calculator for the calculation to make the working faster and avoid careless mistakes. We have the root 1.65 corresponds to 3 significant figures, same as the one from bisection method, and this method takes less steps. To consolidate the techniques learned from the bisection method and Newton method, it is good to apply both methods to solve the same equation for comparison. You may try with other polynomial equations. In fact, these two methods work for not only polynomial equations, but also any continuous and differentiable functions. Here is another example. Solve x squared equals to 2 to the power x for an irrational root corresponds to 2 significant figures. Both x squared and 2 to the power x are continuous and differentiable, and so is the function fx equals to 2 to the power x minus x squared. It is obvious to see that f2 equals 0 and f4 equal to 0. In other words, 2 and 4 are rational roots of the equation. If you sketch the graphs of y equals to x squared and y equals to 2 to the power x, you will see the graphs intersect at a negative value of x. Check that f0 is positive and f of negative 1 is negative. There is a root between negative 1 and 0. You may use bisection method and Newton method to find it out corresponds to 2 significant figures. I put down the answer in the comment of the video for your reference.